Buckle up, everybody, because today we're going headfirst into one of the most mysterious and awe-inspiring things out there, black holes.
Yeah, black holes.
Regions of space-time where gravity is so intense that nothing, not even light, can escape.
It's true.
It's a concept that's captivated scientists and sci-fi fans alike for decades.
And for good reason. They really push the boundaries of our understanding of physics and the universe. We're going to explore not just what they are, but how they form, what types exist, and how we even know they're out there when they're famous for being, well, black.
Right. And trust me, it's way cooler than just staring into a void. We've got exploding stars, ripples in space-time, and maybe even clues to the fate of the entire universe.
The whole shebang.
But before we get ahead of ourselves, let's start with the basics.
Yeah.
Can you give us a crash course on Black Holes 101? What's going on with this whole not even light can escape thing?
Yeah, so it's all about gravity, but on a scale that's really hard to wrap our heads around. So imagine if you throw a ball upwards. It goes up, slows down, and then falls back down because of Earth's gravity, right?
Right. Now imagine throwing that ball with so much force, with so much velocity, that it actually escapes Earth's gravitational pull entirely.
Okay.
That's the concept of escape velocity.
Okay, I'm following so far.
More speed equals a better chance of breaking free from gravity's grasp.
Exactly. Yeah.
Now, with a black hole, the escape velocity is greater than the speed of light.
Oh.
And since nothing can travel faster than light, nothing can escape a black hole's pull once it crosses a certain boundary. We call this the event horizon.
The event horizon. So that's like the point of no return.
Exactly.
Once you cross it, you're committed to whatever fate awaits at the heart of a black hole.
Precisely. And that fate is thought to be a pretty strange place called the singularity.
Okay.
Imagine all the matter of a star, or even more, compressed into an infinitely small point.
I can't even.
That's the singularity, a point of infinite density where the laws of physics as we understand them break down. Okay, that's where my brain starts to melt a little. Infinite density. It's like trying to imagine fitting the entire universe onto the head of a pin.
Right. It's definitely mind-bending. But think about it this way. It's not just that black holes are massive. It's that they pack all that mass into an incredibly tiny space.
Yeah.
That's what creates such extreme gravity. It's like taking that bowling ball on the trampoline analogy and cranking it up to 11.
Right. The bowling ball warping the trampoline fabric is a classic way to visualize how mass warps space-time, creating gravity.
Right.
But with a black hole, it's like that bowling ball just keeps getting heavier and heavier, warping the fabric of space-time so much that it basically creates a bottomless pit.
You've got it. And that bottomless pit with the event horizon marking that point of no return is a consequence of some of the most massive objects in the universe meeting a rather dramatic end.
You're talking about how most black holes are formed, right? It all starts with the death of a star. Tell me more.
So yeah, most black holes are born from the remnants of massive stars that have reached the end of their lives. You see, stars are these incredible balancing acts. They're constantly battling against their own gravity, trying to collapse in on themselves, but they're held up by the outward pressure generated by nuclear fusion in their cores.
Like a cosmic tug of war.
Exactly.
And for most of a star's life, fusion wins, keeping it shining bright. But eventually the star runs out of fuel for that fusion, right?
Exactly. And when that happens, gravity gains the upper hand.
Uh-oh.
For massive stars, this results in a spectacular collapse. The core implodes, and if it's massive enough, that collapse just keeps going until all that matter is crushed into an infinitely dense singularity, a black hole.
So it's like the star goes out with a bang, literally, and leaves behind this incredibly dense remnant that warps space-time like crazy. But you mentioned that this happens with massive stars. Is there a size limit? Could our sun ever become a black hole?
That's a great question. And luckily for us, the answer is no. Our sun is way too small to ever become a black hole. It doesn't have enough mass for its core to collapse into a singularity.
Okay, good. That's a relief.
Yeah.
I was getting a little nervous for a second there.
Yeah.
So our sun is safe from a black hole makeover. But what about these massive stars that do go supernova and leave behind a black hole? What happens to all this stuff that gets too close, and falls in, crossing that event horizon?
Yeah.
Does it just get crushed into oblivion at the singularity?
Well, we can't observe what happens inside a black hole directly because, remember, not even light can escape.
Right.
But things get really interesting when we consider this whole information can't be destroyed idea in physics.
Right. It's like that old saying, you can't make an omelet without breaking a few eggs.
Right.
Except with black holes, it's more like you can't make a black hole disappear without leaving behind some information about what you threw in. But if nothing can escape, Where does that information go?
That's the million-dollar question. And it leads us to one of the biggest head-scratchers in physics, the information paradox. You see, according to our current understanding, black holes should slowly evaporate over incredibly long periods through a process called Hawking radiation.
Oh yeah, Hawking radiation.
Yeah.
That's where things start to get really weird, right?
Right.
We were talking about how nothing, not even light, can escape a black hole.
Right.
So how can something that's supposed to be a cosmic vacuum cleaner actually radiate anything?
It's all thanks to the mind-bending world of quantum mechanics. At the event horizon, the boundary of a black hole, things get fuzzy.
Okay.
Literally. Quantum mechanics tells us that even the vacuum of space isn't truly empty. It's teeming with virtual particles that constantly pop into existence in pairs, only to annihilate each other moments later.
So it's like the universe has a slight case of static with these particle pairs flickering in and out of existence.
Exactly. Now imagine this particle pair popping into existence right at the edge of a black hole. Sometimes one particle might fall in past the event horizon while its partner manages to escape.
Okay. And because nothing can escape from inside the event horizon, those particle pairs can never meet up to annihilate each other.
You got it. The particle that escapes becomes real, carrying away a tiny bit of the black hole's energy. From an outside observer's perspective, it looks like the black hole is emitting radiation, Hawking radiation.
Okay, that is seriously cool. So black holes are slowly losing mass through this quantum quirk.
Yeah.
But you said this ties into the information paradox. What's the paradox here?
The problem is that, according to our current understanding, this Hawking radiation doesn't seem to carry any information about the stuff that fell into the black hole in the first place.
Okay.
Just random thermal radiation.
So it's like trying to reconstruct that book from its ashes, but the ashes are all the same. We lose all the information about the book itself.
Exactly. And that creates a problem because one of the fundamental principles of physics is that information can't be destroyed. Even if you burn a book, shred it, or toss it into a black hole, the information within it should theoretically still exist in some form.
So if black holes evaporate through Hawking radiation, and that radiation doesn't carry any information about what fell in, what happens to all that information? Does it just vanish into thin air, violating the laws of physics?
That, my friend, is the information paradox in a nutshell. It's a puzzle that has stumped physicists for decades, and it has profound implications for our understanding of the universe.
Like that. It's like realizing the rule book we use to understand the universe might be missing a few crucial pages.
That's a great way to put it. And it gets even weirder when we start exploring some of the potential solutions to this paradox.
Oh, I'm all ears. Hit me with your wildest black hole theories.
One mind-boggling idea is the holographic principle. It suggests that all the information contained within a black hole, everything it has ever swallowed, is actually encoded on its event horizon, that two-dimensional surface of no return.
Wait, so you're saying that the 3D information of everything inside a black hole is projected onto its 2D surface, kind of like a hologram?
Exactly. It seems crazy, but think about a hologram on a credit card.
Okay.
It's a two-dimensional surface, but when you shine light on it just right, it creates a three-dimensional image. The holographic principle suggests that something similar might be happening with black holes.
That is some next-level cosmic weirdness. So instead of information disappearing into the singularity, it's preserved on the event horizon like a cosmic hard drive.
That's the idea. Now, another possible solution, and this one is a bit more intense, is the firewall hypothesis. It proposes that at the event horizon, there might be a region of incredibly high-energy particles, essentially a wall of fire, that incinerates anything that tries to pass through.
So it's like a cosmic security system ensuring nothing escapes, not even information.
In a way, yes. Although I should mention that the firewall hypothesis is pretty controversial in the physics world.
Of course, it wouldn't be a proper black hole mystery without a little controversy. But this information paradox, these mind-boggling solutions, they seem so theoretical. Is there any way to test these ideas?
That's the challenge with black holes. They're these incredibly extreme environments, difficult to observe directly, let alone experiment on. But the good news is that we have other ways of seeing the unseeable through their effects on their surroundings.
Right. We talked a bit about how the way a star moves can reveal the presence of a black hole nearby. But aren't there other ways we can detect these cosmic giants? Tell me more about how we hunt for black holes.
Yeah, the cosmic detective work. So we've got stars doing a little dance that betrays a black hole's presence nearby. But what about those black holes that aren't playing tug-of-war with the visible companion? How do we find those lone wolves of the cosmos?
That's where things get even more interesting. One way is by looking for the aftermath of a black hole's rather messy eating habits. Okay, messy eating for a black hole. I'm picturing a cosmic toddler with spaghetti sauce everywhere. What does that actually look like?
Think of it more like a cosmic whirlpool. When material like gas and dust gets too close to a black hole, it doesn't just fall straight in. Instead, it spirals around the black hole, forming this superheated disk of matter called an accretion disk.
So it's like the universe's most extreme roller coaster ride where everything is spiraling down the drain. A drain with a black hole at the bottom.
Exactly. And as this material spirals inward, friction heats it up to millions of degrees, causing it to emit intense radiation, including X-rays. And we can detect these X-rays from Earth, revealing the presence of these hidden black holes.
So even though we can't see the black hole itself, we can see the glowing beacon of its cosmic feast. And speaking of seeing the unseeable, how did we go from detecting these X-ray signals to actually capturing an image of a black hole's shadow? That seemed impossible for the longest time.
It was a monumental achievement, and it all came down to a revolutionary telescope, the Event Horizon Telescope, or EHT for short. It's not your typical telescope, though. It's actually a network of radio telescopes scattered across the globe, all working together to create a virtual telescope the size of Earth.
Wow, a planet-sized telescope. That's some serious astronomical teamwork.
Yeah.
What's the advantage of having such a massive telescope?
It all comes down to resolution. The ability to see fine details. The bigger the telescope, the better the resolution. And to image something as small and distant as a black hole, you need incredible resolution. The EHT essentially turned the entire Earth into a giant radio dish, allowing astronomers to capture that historic first image of a black hole's shadow back in 2019.
That image was truly awe-inspiring. It really brought home the reality of these objects that were once considered purely theoretical. And now you're telling me we can actually listen to black holes too. Tell me more about these gravitational waves.
Right, so gravitational waves are like ripples in the fabric of space-time itself,
Whoa.
generated by some of the most cataclysmic events in the universe, like black holes colliding. Imagine two black holes locked in this death spiral, spinning around each other faster and faster until they finally merge in a burst of energy. This cosmic collision sends out waves of distorted space-time that travel outward at the speed of light.
So it's like the universe is ringing like a bell after these massive collisions.
Uh-huh.
How do we even detect these space-time ripples? It's not like we can just stick out our hand and feel a gravitational wave pass by, right?
You're right, these waves are incredibly subtle. To detect them, we need incredibly sensitive instruments called interferometers.
Okay.
Observatories like LIGO and Virgo use lasers and mirrors to measure these tiny stretches and squeezes of space-time caused by passing gravitational waves. It's a feat of engineering and precision.
It sounds like it.
Yeah.
And what have we learned from listening to the universe's symphony of gravity?
Well, gravitational wave astronomy is still a young field, but it's already revolutionizing our understanding of black holes. By studying the shape and frequency of these waves, we can determine the masses and spins of the black holes that created them, confirm their existence in distant galaxies, and even learn about the properties of gravity itself in these extreme environments.
It's like gravitational waves are giving us a whole new sense with which to explore the universe. We've talked about seeing their effects on light and matter, and now we're listening to their whispers across space-time. This is all just mind-blowing. It really makes you realize how much more is out there to discover.
Absolutely. And the most exciting part is that this is just the beginning. With new telescopes being built and gravitational wave detectors becoming even more sensitive, who knows what other secrets of black holes we might uncover in the coming decades.
It seems like every time we answer a question about black holes, we uncover a dozen more mysteries. But that's what makes them so captivating. They remind us that the universe is this vast, strange, and wonderful place full of surprises. And we've only just begun to scratch the surface of its secrets. So to our listeners out there, if this deep dive has sparked your curiosity, I encourage you to keep exploring. Read up on the latest discoveries, listen to podcasts like ours, and never stop asking questions. The universe is full of wonders just waiting to be discovered, and maybe, just maybe, you'll be the one to unravel the next great cosmic mystery.
For more short-form podcasts like these, please like and subscribe. The top comment on this video will be the topic of our next podcast. Goodbye.